In this video, I'm going to introduce what's called the Zimm plot, which is probably the most thorough way of analyzing light scattering measurements. So I'm going to show you some data in a second, and it's for light scattering measurements that were done from methyl cellulose. And these measurements were performed at 20 degrees C with an argon laser that has a wavelength of 488 nanometers. Now think to yourself why that information might be useful. Now under these conditions, the refractive index of water, which of course depends on the wavelength of light, is equal to 1.33, and DNDC is equal to 0.137 milliliters per gram. So the problem here, and what we're going to have to use the Zimm plot for, is determining what is the molecular weight of the polymer, what is the second virial coefficient, so how is it interacting with its surroundings, namely the solvent, and what's the size of the polymer, what's its radius of gyration. And to find these values from light scattering measurements, we have to use Zimm's equation. Because what Zimm's equation does is it doesn't assume anything about the angular dependence of a polymer, other than, that of a polymer. Nor does it assume anything about the concentration, nor does it assume anything about the value of the second virial coefficient. But you can see how it's written here. Using this equation is kind of problematic. One reason for that is that K times C divided by R theta is actually what we measure. And so what's on the left-hand side of this equation, shown in the box here, is K times C divided by R theta. But that variable C is appearing on both sides of the equation, so that's a little bit problematic in and of itself. But just like with osmometry, and with the simple light scattering that we've already discussed, 1 over the molecular weight can be determined based on the value of the y-intercept. But the problem with just finding the y-intercept is that both Q, the scattering vector, or in other words, the angle, is changing. And at the same time, we need more information. We need multiple concentrations if we want to get the value of the second virial coefficient. So the first thing we need to do is, if we want to know what the molecular weight is, we have to extrapolate the measurements that we've made to the case where the concentration is equal to 0, so that the second virial coefficient terms disappear. And we also have to extrapolate to Q equals 0, so that we have no angular effects, and so that the radius of gyration does not appear. And that will give us just the molar mass if we do that. So hopefully you can see that if you let Q go to 0 and C go to 0, you get the equation that we have above. So if we get the y-intercept, because that will happen when Q is equal to 0, and let the concentration go to 0, then we'll get 1 over the molecular weight, and we can solve for that. Now, once we get that value for MW, we can let the concentration go to 0. So if we can extrapolate to the case where concentration is equal to 0, then all that we're left with is what's in this red box here. And you can see that if we plot Kc divided by R theta as a function of Q squared, that we can fit this, and what we'll obtain from the slope is Rg squared. And then finally, if we let Q go to 0, then our data Kc divided by R theta will be equal to 1 over the molecular weight plus 2 times the second virial coefficient times concentration. So then if we fit this data as a function of concentration, then the slope of that line will give us 2 times the second virial coefficient. Now I hope I made this clear, because what we're having to do here is a double extrapolation. We have to first extrapolate to 0 concentration and 0 angle, so Q equals 0, to get the molar mass. Then, using this data, we can use 0 concentration data to get Rg squared, and then we can look at the 0 angle, so Q equals 0 again, and fit the data as a function of concentration to get the second virial coefficient. Then we have to extrapolate to get 0 concentration and 0 angle data, because we can't measure either of those by themselves. In other words, we can't measure light scattering data for 0 concentration because we wouldn't get any scattering. We have to measure a polymer, so we have to extrapolate to get that information. Secondly, we can't measure light scattering for Q equals 0. That's 0 angle. The reason we can't do that is because at 0 angle, we'd be staring down the laser beam, and we would only be seeing the laser light that's coming to us and not the scattered light. So we also have to extrapolate to see what the scattered data would look like at Q equals 0. So as you can see, it's not such a simple problem. We have to approach this in multiple steps, and that's the utility of the Zimm plot. And I'm going to show you some tricks of the trade as we make this plot. So on the following slide, I'm going to show you this actual light scattering data and show you how to go about analyzing the data to get these very important quantities. Now, this is real data. This is from a paper in 1999, actually when I was still in high school. From Tim Lodge's lab. Tim Lodge is a very well-known chemical engineer and chemist who's at the University of Minnesota. And what he was looking at with his group was methyl cellulose. In fact, Professor Morozova in our department also worked quite a bit with methyl cellulose when she was working with Professor Lodge. So you can see the chemical structure and you can see the front page of the paper here. So all of this data comes from this study from, 21 years ago. So here are the results of light scattering measurements. And what you'll notice is that, first of all, theta, the scattering angle or the angle at which the scattered photons were collected, varies from 0 to about 150 degrees. That's about normal. That's what my instrument would do. But you'll notice that there's no data for theta equals 0 because that's impossible for us to measure. The scattered photons are so weak compared to the incident photons from the laser that we can't measure this. And you'll notice that we have no data for zero concentration because we can't measure scattering from something that doesn't exist. So we have to extrapolate to get both this data and this data. So the first thing I can calculate here is the sine squared of theta divided by 2 because I can calculate Q from that. So here I'm going to calculate that. It's the sine. Theta is A3 divided by 2. And notice that the angle is given in degrees, and that's not going to work here because this function is expecting radians. And so there are pi radians in 180 degrees, and we want sine squared of theta divided by 2, so I'll just multiply this by the same thing. Okay, so now that we've done that, we can fill down. And now we have all of the values of sine squared of theta divided by 2. And we still can't get this data, and we still can't get this data. So now we're going to have to fill in the values for this intercept. Okay, so let's start to get this information for zero concentration. Now, how can we do that? Well, what we'll do is we'll plot the concentration. Actually, we'll plot the light scattering data as a function of concentration. So this will be the data for the lowest concentration of 0.21 mgs per mil. And so I can add that to the scatter plot, and now you can kind of see what the data looks like. So on the x-axis here is sine squared of theta divided by 2. And on the y-axis here is the light scattering data for 0.21 mgs per mil. And so I'm just going to click on this. I'm going to add a trend line because we're going to want to fit it. And it's going to be a linear fit. I want to display the equation on the chart. And we can display the r² value if we really want. But notice what this means. I know this is kind of hard to see here. But if I click on the information about the line of best fit, you see I've got slope plus y-intercept. So that means for this data here, the y-intercept will be 3.42. And that makes sense because also you'll notice as we go to higher and higher angle, this value kc divided by r theta is increasing. Now we could go back here and click on this graph and we can add more data if we want. So this first series that we had here was for a concentration of 0.21 milligrams per milliliter. And what we can do is we could add another set of data if we want. So the next concentration that we have is 0.30 milligrams per milliliter. And of course, the x values are going to be sine squared of theta divided by 2. And the y values are going to be the light scattering data for this concentration. And that should append it to the plot. And here it is. Notice how close this data is. It is so hard to see the difference between one concentration and the other. And I'm going to keep adding all of the concentrations to this plot now, just to show you what it's going to look like. So again, I've got more concentrations to add, so I can add the concentration of 0.5 mg per mil. The x values will still be sine squared of theta divided by 2. And the y values are going to be the light scattering data. And there we go. So you see, here's the next set of light scattering data. Just a very, very subtle change. And let's add in the last one. So the last concentration that we have is, let's see, 0.59 mg per mil. The x values here are all of these. And the y values are all of these. So you see it's going to look very similar to what we already have on here. Okay, so now we just need to get the rest, right? Because we've got the zero angle scattering for this concentration, so we just need to go up and get the rest of them. So I'm going to add a trend line for this, and hopefully this doesn't get too hard to read, although I can see already that it is. Okay, so the scattering for the second line here, the second concentration, at zero angle, I know it's kind of hard to see, but it's 3.62. And we've just got a couple of concentrations left. Click on this, add a trend line, display the equation. The scattering here, you can see from this is 4.03. And finally, scattering here, we can look at, we can add a trend line, we can display the equation. This is really jumbled up, but it's 4.13. So now you see we've extrapolated to see what happens because sine squared of theta divided by 2 is equal to 0, what the angle is equal to 0. And so by extrapolating to what the y-intercept is here, we've found what the scattering angle is right in front of the laser, even though that's something we can't see experimentally. So now we have that data. So what we've got here is basically light scattering as a function of concentration, and there's going to be no Q dependence there. So what does that mean in terms of our Zimm equation? Well, if there's no Q dependence there, then if we can get the data for zero concentration, then we should be able to get information about the molar mass. Look how we can do that. So this data here going down the column is scattering as a function of angle. If we look across though, this is scattering intensity as a function of concentration. So each of these rows represents scattering at a certain, how do I want to say this? At a certain angle. So we can get the concentration, the information on the light scattering at zero concentration by going through and doing regressions on every single one of these angles. So let me show you. Let me get rid of this plot because we don't need it anymore. And we're left with our data. So how on earth are we going to get this? Well, we're going to have to put in our concentration. So we have zero concentration, 0.21 mg per mil, 0.30 mg per mil, 0.50, and 0.59 mg per mil. And so what we're going to have to do is, here's our data. So this is at this is our, how do I want to say this? This is at 0 degrees right here. So again, this is concentration. This is 0 degrees, and this is going to be the light scattering data here. And you know, I'm not being the neatest with doing this, and when you do your project, hopefully you get this much more organized than I'm doing, but I want to show you what this looks like. So here's 3.42, that's this value here. The next value will be 3.62, 4.03, and 4.13. So 3.62 goes here, 4.03. Sorry, we don't know this value. This is what we're trying to find. 3.62, 3.42, 3.62, 4.03, and 4.13. So if we plot this, we're going to plot the light scattering signal as a function of concentration. And if we do a linear regression on that, oh good, it's linear still, as it should be. And if we extrapolate this to concentration equals 0, then we'll get that value. So again, this is hard to see, but the y-intercept here is 3.0369. So that means this value here is 3.0369, so we'll make that a 7. And does this make sense? Well, yeah, it does make sense because the scattering should increase as we increase the concentration, and the scattering should increase as we go down the column. So this makes a lot of sense. So we're going to have to do this for 0, 30, etc. So we can go in and we can do the same thing again, 30 degrees. Concentrations, and let me actually put in this value here. This is 3.037. I guess this should be 0.04 if we want to keep our significant figures here. And I can do the same thing. I can copy this. This will go here. And now I have to copy in the 30 degree data. So here's 30 degrees. So 3.61 goes here because we don't know the value for 0 concentration. 3.87, 4.21, 4.29. And I can add it to this graph, create a new series. The x values are going to be the same. And the y values will be these. And there we go. So again, it's kind of hard to see, but we can do the same kind of extrapolation. And so if we do this, we can add a trend line, display the equation. And so this data here, again, hard to see, I'm sorry, but the y-intercept is 3.287, so 3.29. So this data here will be 3.29. And that means this data here will be 3.29. And we're going to have to, again, do it for every single value here. All right? So I'm going to keep doing that. I'm going to keep plugging away. Let me move the chart up here so that it stays out of our way, and then we'll do it again. So next is 40 degrees. And now, through the magic of television, I'm going to spend 18 minutes doing this for every angle, plotting the data, fitting the data, getting what the scattering would be at 0 concentration by extrapolating, and filling in the values. And so it takes a bit of time, as you can see. And so I'll just speed it up so you get the idea of how it's done. So at this point, I've done 2 extrapolations, and I'm showing the most recent one here. But what I did is I plotted on the x-axis the scattering angle, or actually I plotted sine squared of theta divided by 2, so that's this column here. So these are my x values. And then I plotted every single concentration. So I plotted this data, and this data. And I looked for the y-intercept. And the y-intercept gave me the scattering intensity at 0 angle. That is, if I'm looking at the laser, what's the scattered intensity? And that's something that I can't measure. It's impossible to measure that. The next thing that I did is for every single concentration, I used these concentrations on the x-axis. And then for each angle, of course, I didn't have to do 0, but for every other angle, I plotted these values here as a function of the concentrations. And that's what you're seeing in the plot here. And what that allowed me to do was get all of the data in this column, which is the scattering with 0 polymer. And there's a scattering with 0 concentration, which again is something that I can't measure. So I can put it all in a graph like this. And now I've labeled this. This is the data that I got. This is the one column that was really hard to get. And this was the other column that was hard to get. So I have, again, scattering looking at the laser, which I can't measure, and scattering with 0 concentration, which is right here. So let's plot all of these. So this is going to be my x-axis now. I'm going to plot on the x-axis sine squared theta, and on the y-axis the scattering intensity for each of these concentrations. So let's first do that. So I'm going to insert this, new graph. I'm going to blow this up, and I'm going to label this actually. I'm going to call this Mike's Bad Zimm plot. You're going to see it's not actually that good. So here it is. And this was here for 0 milligrams per milliliter polymer concentration. And now I'm just going to add all the rest of the data to this graph. So I'm going to add 0.21 mgs per mil. Of course, the x-axis, these values will still be sine squared of theta divided by 2. These values will be here. I've got that data. Let's go ahead and add the rest of them. This is 0.30 milligrams per milliliter concentration of polymer. Got the sine squared theta on the x-axis. Scattering intensity on the y-axis. 2 more. So 0.5 mgs per mil. X-axis, all of these values. Y-axis, all of these values. And the very last one, 0.59 milligrams per milliliter. And we'll just select the correct data here. Got that and that. All right, now let's see what it looks like. Here it is. Here's my bad Zimm plot. There's a couple problems here. This is 0 concentration at the bottom. This is the extrapolated data as a function of angle. This point here, there's one point right there where you see my cursor. That is the y-intercept, and that is 0 angle, 0 concentration. So the molar mass is proportional to this point here. In fact, it's 1 over that. So I've got that. Then these are the data for every single angle. And now the data is all bunched up on top of each other, and you see that I've got different concentrations here and different Q values, and it's a real jumbled mess. So that's why I say it's not such a great Zimm plot. In fact, it's not a Zimm plot, but it's kind of like one. So I'm going to put this up here so that we can compare. And now when I do this, and even when I do this as a researcher, I can plot this data any way that I want. So why don't I start to offset the x-axis a little bit? What do I mean by that? Well, let's go to a concentration of 0 milligrams per milliliter. And then instead of sine squared of theta over 2, let's put a little offset in here. So let's make this equal to B3 plus, and then I need a number out front. So plus the concentration, which is 0, times, what could I make this? I'm going to make it 3,000. I'm going to tell you why that is in a second. But I can fill down. In fact, these last 3 values I don't need. And that's going to be sine squared theta. Let me just write it in here. This is sine squared theta divided by 2 plus 3,000 times C. And that's for a concentration of 0. Of course, I could do the same thing here. Let me space it out. This is a concentration of 0.21, concentration of 0.30, concentration of 0.50, and a concentration of 0.59. And so this is equal to B3 plus 3,000 times the concentration, which is 0.21 mgs per mil. That's kind of big, right? 630. It's going to really space this out. So I can either decrease the value here to something more reasonable, which I think I'm going to do. So I'm going to make it 30. And then I get 6.3. So that's kind of nice. Basically, this data here is going from 0 to 0.93. I didn't want this data here to go all the way out to 600. So I think that works nicely. We'll make that constant 30. So here's that data, and this is going to be B3 plus 30 times the concentration, which is 0.3. So that'll give me 9, and I'll fill down. And this is going to be equal to B3 plus 30 times 0.5. Fill down, and then the very last one. So this is equal to B3 plus 30 times 0.59. So now these will be the values for my x-axis. These are going to offset the data. And you can kind of see how that is. This should be plus, not times. Okay, so everybody should increase. And now I'm going to plot the data. So I'm going to take this bad Zimm plot here, and I'm going to make a new Zimm plot. So I'm going to plot, these are my values on the x-axis. These are the corresponding light scattering data. So I will make a new scatter plot. And that's not quite what I wanted at all. So let's delete the data and do this manually. I really screwed this up. This is why professional scientists don't use Excel. We use Origin or XMGrace or something like that. Okay, let me just get this started here. There's the X values and the Y values. Clearly, Microsoft Excel was not written for scientists. In fact, clearly Microsoft Office was not meant for scientists because it's so terrible. Okay, so now I'm just going to add the rest of the data here, just like I did before. So this was concentration of 0 mgs per mil. And now let's add in 0.21 mgs per mil. And let's select the X values. These are going to be the X values here. And we'll select the Y values. Those are going to be these ones here. And let's just stop and make sure it looks okay. It does look okay. So you see how doing that has shifted the data horizontally. And now the lines are more distinct from each other. And I'm going to keep going. Basically, shifting the data like this allows you to have both angle and concentration on the x-axis, right? Because it's sine squared of theta divided by 2. Theta is my angle. And then it also incorporates the concentration. So this is both variables. So now I'm just going to keep adding the rest of the data here. So I'm going to add 0.30 mgs per mil. X values, those are going to be these. And the Y values are going to be these. And just two more, so bear with me. 0.50 mgs per mil. X values. Y values. Oh, and one more, thank God. As I'm doing this, I'll just say that, again, in the real world, the instruments these days will make the Zimm plots for you, but it's really instructive to see what they actually are, because just plugging into an instrument, just saying, oh, well, the instrument told me that this is the number, this must be the molecular weight or whatever, that's really dangerous. You can get into a lot of trouble that way. So I really encourage you not to do that, and that's why we're going through the Zimm plot like this. Okay, so here's a good Zimm plot, because now I've got both concentration and angle taken care of on the x-axis here. I have the different concentrations here, and I actually have different angles going up like this. And I'll explain what I mean by that in a second. But for now, let me start drawing some things on this plot to explain to you what it's meaning, like what it's telling us. And in my opinion, the Zimm plot is actually a very clever construction for analyzing light scattering measurements. Okay, so each of these sets of lines represents a different concentration. So starting on the left, we have a concentration of 0 mgs per mil. Remember, that's not something that we can measure. And then progressing over to the lines as we go towards the right-hand side of the plot, we're increasing the concentration. And because we've offset the axis like that, this allows us to separate out the effects of concentration from angle in this way. You'll notice the bottommost points are linear, And these points represent data taken at a scattering angle of 0 degrees. And as you move to the right, as you get to larger values on the x-axis, this corresponds to higher and higher concentrations. So looking at this all together, I want to show you the two sets of data that we've extrapolated here. These bottom points, again, are the extrapolation to 0 scattering angle. And that was the first thing that we did by plotting each concentration individually and looking for the y-intercept as a function of sine squared of theta over 2. The second extrapolation was for each scattering angle. We plotted the data as a function of concentration on the x-axis and found the y-intercept. And that gave us the data that's highlighted here, which is the scattering from a concentration of 0 mg per mil, which again is not possible because you can't measure scattering from something that doesn't exist, right? You have to have a non-zero concentration. And then finally, these two lines, as you go across, again, moving across the x-axis to larger and larger values moves you up to higher and higher concentrations. And then as you move up vertically, you're going from a scattering angle of 0 degrees at the lowest limit to a scattering angle of 150 degrees at the very highest set of points. And so the connection, these red lines that I'm showing here, are lines of constant scattering angle, and that's how the scattering is varying as the concentration increases. So there's a lot of information on a Zimm plot. And now the task that we have is how do we use this information to get values out for the molecular weight, second virial coefficient, and radius of gyration of our polymer. So the first thing I'd like you to notice before we do this is that both sets of lines, either concentration equals 0, the fits to that, or Q equals 0, or theta is equal to 0, the fit to that, notice that they both have the same y-intercept. So that's, first of all, important. Secondly, the slope of one of these lines, that is the concentration line, will give us the second virial coefficient. The slope of the other line at theta equals 0 will be related to the radius of gyration. Okay, so realizing that everybody has the same value for the y-intercept here, notice that going across at a constant angle of theta equals 0, notice that there's only 4 points corresponding to the 5 points corresponding to the 4 concentrations that we measured and the 1 concentration that we extrapolated to. On the other hand, for a fixed concentration, in this case for 0 concentration, but looking at multiple scattering angles, again, the two curves, this curve here and this curve here, have the same y-intercept, but notice that there are much more points at a constant concentration than there are going this way. So in my opinion, it's better to fit this data because in this case, we've got more points, and so hopefully we can get a better least squares fit. So what I'm going to plot on the x-axis again is going to be our scattering vector, or it's going to be related to our scattering vector, which is sine squared of theta over 2. And I'm going to plot against that the light scattering data for 0 concentration. So let me insert the graph. Linear, no big surprise here. And I'm going to fit this data with a trend line. Again, it should be linear so that I can get the y-intercept. And notice here, I'm in fact even going to make this bigger so that we can all see it. Notice here that the y-intercept is 3.0348. So we're going to call the y-intercept here. Let's keep our significant figures in this case. Let's keep it at 3.03. But notice up here, notice what the y-axis is. It's kc, k times c divided by r theta times 10 to the 6. So what that actually means is that our y-intercept here is not 3.03, but it's 3.03 times 10 to the minus 6. So that's our value of the y-intercept. We got it from our least squares fit. And now with that, it's time to calculate the values that we're interested in. Okay, so here we go. So to remind you, the y-intercept, and it doesn't matter which line we use to get this, the y-intercept will be 3.03 times 10 to the minus 6th. And I said nothing about the units so far. Now, if you wanted to figure out the units, what you could do is you could go through, figure out what K is, get units of concentration, so on and so forth. I'm just going to tell you what the units are in a second. But Kc divided by R theta is equal to 1 over the molecular weight averaged, plus 2 times the second virial coefficient times concentration, plus ... And this is only if Q is equal to 0 or if theta is equal to 0 degrees. Those are both the same things. That's the same statement. So if the concentration goes to 0, that second virial coefficient term isn't going to matter very much. So Kc divided by R theta will be 1 over molecular weight. And that intercept is equal to 3.03 times 10 to the minus 6th. So if that's the case, then the units of Kc over R theta must be moles per gram. Because if we put that y-intercept into here, well, we get a molar mass. The molar mass, or the molecular weight, is grams per mole. So we can evaluate this numerically. We can just plug it into our calculator and get a value for what this molar mass is. And again, if I didn't know the units, I could go through and work it out, but I'm going to save us some time here. So the molecular weight will be 3.3 times 10 to the 5th grams per mole, which means that Kc divided by R theta must be moles per gram. Right? So that answers the unit question right there. Moles per gram is the unit of Kc divided by R theta. Okay, so whichever approach you take, whether fitting as a function of concentration or fitting as a function of Q, you're going to get the same y-intercept as I showed. But if we want the second virial coefficient, remember from Zimm's equation that we need Q equals 0 to simplify the term with the form factor, and we need the scattering data as a function of concentration. So for this part of the analysis, what we really need are these concentrations 0, 0.21, 0.30, 0.50, and 0.59. And we need to plot, as a function of those concentrations, the scattering intensity. So that's what I'm doing here. And then once we do that, then we need a least squares fit. Okay, so x-axis is concentration, y-axis is scattering intensity, or related to scattering intensity. So I'll make the graph a little bigger here. And we can fit this, add a trend line, show the equation, and I'm going to make this bigger so that we can see. So what do we see here? The slope is 3.04 times 10 to the minus 6. So we do get the same slope. Sorry, same y-intercept is 3.03 times 10 to the minus 6. The slope here is different though. The slope is 1.90. So the slope is 1.90. And actually that's also times 10 to the minus 6 for the same reason as before, right? Up here, we're looking at that scattering information, but multiplied by 10 to the 6 because the values are so small. Okay, so now we've got the slope. So from the slope, what we can do is now calculate what the second virial coefficient is. So the slope was 1.94 times 10 to the minus 6th, and we have the units issue again. We'll have to figure out what the units are. This time I'll actually go through it though and show you a little bit. But remember, Kc divided by R theta is equal to 1 over the molecular weight plus 2 times the second virial coefficient times concentration plus higher order terms in the case that the scattering angle theta is equal to 0, or Q is equal to 0. So 2 times the second virial coefficient then should be equal to 1.94 times 10 to the minus 6th, which means that the second virial coefficient is just that divided by 2. So B2 is equal to 1.94 times 10 to the minus 6th divided by 2. So 9.7, I guess, times 10 to the minus 7 is the answer. So what are the units? The units are very important because there are some second virial coefficients that are renormalized so that they have no units. And this one does have units. And when you use these in theories and when you try to analyze your system, you need to make sure that it's the right units. So Kc divided by R theta has units of moles per gram. And 2 times the second virial coefficient times the concentration must have units of moles per gram. Now we knew what the concentrations had units of because that was milligrams per milliliter. So this tells us basically what the units of the second virial coefficient must be. And the reason for that is that milligrams per milliliter times the second virial coefficient, whatever those units are, must give us units of moles per gram. And so we can just solve this equation and get units. Now, we've got milligrams over here, we've got grams over here, so our best bet is to convert everything to grams, just so that we have the same units. So if that's the case, the units that we're looking for here are going to be moles per gram, and then divided by the units of concentration. So we'll get 1 over milligrams. And then in the numerator, we'll get milliliters. And so if we convert the milligrams to grams, then we're going to get moles times cubic centimeters, because that's the same as a milliliter, and then times grams squared, right? So we have to multiply our number by 1,000 to get rid of this milligrams. So the final answer here for the second virial coefficient, this will be equal to 9.7 times 10 to the minus 4 after we multiply by 1,000, right? So 9.7 times 10 to the minus 4 moles times centimeters cubed divided by grams squared. Okay, so following the scattering intensity, or Kc divided by R theta, as a function of sine squared theta over 2, gives us the other slope, 4.82 times 10 to the minus 6th. Now remember that this is equal to 1 over the molecular weight times 1/3 times Q squared times Rg squared plus higher order terms. And then that's it, in the limit that the concentration is equal to 0 mg per mil. So this term here is the y-intercept. And this term here is related to the molecular weight times the slope. Now we have the slope, so hopefully we can get Rg from this, or actually Rg squared. And so this is equal to 1 over the molecular weight, and then times the part in the parentheses that has the slope with it. So multiplied by Rg squared divided by 3, that's the slope, because Q squared is our variable. So that's 4.82 times 10 to the minus 6th. But Q itself is 4 pi and for light scattering times n, the refractive index, divided by lambda, that n doesn't appear for neutron scattering, times the sine of theta over 2. So q squared is 16 pi squared n squared divided by lambda squared times sine squared of theta over 2. So that factor out front, the lambda squared, 16 pi, whatever, we're going to have to multiply by that because we didn't take it into account when we were fitting. So this means that Rg squared is going to be 3 times the molar mass times the slope, 4.82 times 10 to the minus 6th, and then times the stuff that we left off. The lambda squared divided by 16 pi squared, etc. So this will all be multiplied by 1 over this, right? Just because we're solving for that. So in the parentheses, we're going to get wavelengths. Well, let's just write the non-squared version. So the wavelength in the numerator, that's 488 nanometers. In the denominator, we'll get 4 pi times the refractive index, which is 1.3, and then that whole thing will be squared. So just to remind you, refractive index for this system is 1.33. That will change depending on your solvent. And this was the wavelength of the laser, which will also change. My instrument, that wavelength is in the 540 nanometer range. But regardless, we plug everything in, and we'll get 4,073 nanometers squared for Rg squared. The units are set by the unit of the wavelength. So we can easily take the square root of this, and we get the radius of gyration is about 64 nanometers. And so that's it for this video. I encourage you to watch this very slowly and work along with me, because this is a very important skill, being able to analyze scattering like this. So like I said, though, once you do this by hand, you know what's going on. You'll know good data from bad data by being able to just look at the trends. So you'll know if your Zimm plot makes sense. But a lot of times the software does this for you these days. But I want you to look at the amount of effort it takes to analyze light scattering data properly. And when we get to X-ray scattering and neutron scattering, I want you to see how much easier in many instances it can be than analyzing light scattering. They're all important techniques. They all have their place, but some are more straightforward to implement than others.